Hey everyone, and thank you for joining for another episode of Raspberry Pi Pico Emulator live coding. And I can see we have Steve here, and Valeria will watch offline because Italy, Spain apparently has better interrupt priority. Yeah, I totally get it. Anyway, let's see. I think last time we did the USB, so we almost got it to work, or at least I would like to think we almost got it to work. Let me share my screen and see what we did last time, because I don't really remember. We had this file. Let's open it in its own tab. Where we wrote some notes, and yesterday I found this note about a typo in the datasheet, so I actually went ahead. We found a small typo in the datasheet, and I submitted an issue yesterday, and they said they fixed it, and it will go into the next datasheet SDK release. Cool. Other than the simulator, we're also making the Pi Pico documentation better, and that's cool. All right, so I think last time we tried to get the USB CDC, so there was this Hello USB program, and we wanted to see if we can get it to print stuff, and it seems like yeah, we had something. I don't know if we were debugging. Yeah, we were debugging the actual Raspberry Pi, and we were looking at this IRQ probably to see what happens there. Yeah, we probably wanted to print the value of the setup packet because we wanted to simulate that. And then let's just, no, I don't want to open this folder. I just want to run the code and see if, let's make the font a bit bigger. Yeah, it's running, it's waiting for GDB. So let's GDB and yeah, and see if we get stuck or something like that. Oh, it exit. So, yeah. QSBI. Yeah, there are a lot of unimplemented writes to the USB peripheral. But how did we get into exit? We had a panic. Interesting. Oh, wow. Yeah, that's nice to start a stream with a panic. Let's try to figure out see if we can figure out the panic. EP was already available. All right, so this happens is inside a tiny USB. In this function, let's try to see what makes us panic there. Don't remember we had a panic last time, but yeah, I guess we are doing something bad, but what is that? If control available, and what is the value for EP and endpoint number and direction? Not sure. And probably, yeah, we can't see the actual message for some reason. Probably because we don't have the USB output to see it. But yeah, it seems like there is something that the code expects and doesn't happen the way it expects. And let me see. Let's check. Let's take a look at the log and see. Oh, by the way, another small fix. That's a typo I did in one of the previous live streams. So I just fixed it also yesterday, I think. One of the Pi Pico deep dive course pointed out that there was this issue with the interrupts not firing correctly, and apparently we had this stupid copy paste mistake where reading from IRQ1 in status thread from use the IRQ0 variable, like the interrupt enable and force instead of IRQ1. So simple fix, stupid copy paste mistake. I actually spotted the very moment in the stream where I made this mistake. So if you want to see it happening live, I posted a link on Twitter and also in the Discord server. Yeah, anyway, let's see if we left any information from last week. Yeah, so we need to send a set device address setup packet, then send a set device configuration setup packet, and then implement serial over USB. Process control request in USB d.c. So yeah, so we probably get here and we need to send this set address request and then probably set configuration just to configure the USB device. Let's try to restart it and set a breakpoint here to see if we, oh no, we wanted to restart the whole thing. Yeah, and then break here and continue, and yeah, we got into process control request, and that's probably where things go wrong, because we just probably sent an empty packet here, so it probably gets some garbage there. So yeah, we can see that it goes into this switch, and then where are we? 706. Yeah, it thinks this is a get status request. Probably this is 0 or something like that, and that's why it matches. Yeah, but we actually want to send set address request. So let's try to forge this request here and see if we can get it to set the address. I think that was inside USB, and then we had like this code that set device address that sets a flag that indicates to the USB peripheral that we have, or to the code that the USB peripheral has received a new packet, but we still need to write this packet here. So I think we have like this CP RP2040. We had like a buffer, probably USB DPRAM, which is mapped to this address, and then we can just set setup packet, and let's create a setup packet. Let's see. So what should this setup packet look like? I also remember we had this reference with which was linked from the datasheet with a lot of information. So maybe here inside protocol we will have information about this. Yeah, setup packet. Okay, that's what we need. Pretty small. I will try to enlarge this. So yeah, this is like 1 byte, 1 byte, 2 bytes, 2 bytes, and 2 bytes. So maybe so yeah, this is like 8 bytes. So let's create a function that will create this private write setup packet, and let's just include the fields that we have here. So we have direction, type, recipient. Yeah, maybe I will just params setup packet params define an interface, because it's too many parameters to pass on the interface. Yeah, to pass as arguments. So let's define them. So there is like a request type, which is there is like host or data direction, and then there is type, and then there is a recipient, and then we have request. Maybe we'll keep them consistent, the names, with the USB specification. W value number, that's actually 16 bits. We need to see if it's little or big Indian. W index number as well, 16 bits, and W length number, 16 bits. Yeah, I'm not sure about if the data stage should go right, like if this length should go, is the length of data that should come next to this header, or is it like the data stage is another stage? But yeah, I think let's see, set address. So set address is simple. Is there like an example of the set address packet? Set address. Yeah, I don't see something that looks like example. Yeah. All right, so let's try to just create this function, and then we'll figure out the values from the SDK code from TinyUSB. So this dot, so let's create a setup packet as a uint8 array. It's 8 bytes, and then setup packet. The first byte is just a combination of, where was that? Data direction is like params.data direction shifted by 7. It's the highest bit, so maybe we can also define an enumeration for that. Const data direction. So there is like host to device and device to host, right? 0 and 1, and enum not const, enum setup type, and the setup could be standard, class, vendor, or reserved, even though we shouldn't care about this. And then there is like enum recipient, which is the device, interface, endpoint, or other. Okay, so that's setup recipient. And yeah, the other values are reserved, so we should probably not care about them too much. And then we can just make this a bit more friendly by just using the specific types. Setup recipient without a V. And then we can go on to encode a setup packet, so the data direction, and then we have params dot, the next one was type, and that would be shifted by 5, I guess, right? Yeah. And then we have params dot recipient, that's the lowest bits. And then the next one is just the request, packet1 equals params.request. And then we have those values which we need to figure out if they are little or big Indian. And I don't think this says USB setup packet big Indian, but Google can probably answer about that. USB is little India, nice. Cool. So yeah, we can probably just encode it ourselves. So setup packet2 equals param, and then we have the next one was a W value shifted by, oh, we want the low byte and then the high byte. So that's 3, and then I'm going to make another stupid copy paste mistake maybe, but insert sequential starting from 4, and then this would be W index. So please check me, see if I'm not making any stupid copy paste mistake here. Anyway, so the last thing we want to do now that we have the setup packet, we can just copy it to this.rb2040 to the beginning of the USB DP-RAM where we have seen last time or so, I guess. The code is expect to find it, and voila, we got the setup packet, and then we can try to write it here. So this.set device or write setup packet, and then let's see. So I guess the data direction should be host to device because we are sending this to the device, and then the type, I don't know, USB data set address packet example, maybe. USB set address packet example. I couldn't be more specific than that. So yeah, so first of all, I can see like the standard device request codes, and there is like this set address, which is 5. So that's the request code. Request USB request set address, and let's define this enum as well. Setup request may make more sense here. So get status, and we have clear feature reserved. And actually, we are ending up writing set feature. We will end up rewriting tiny USB in JavaScript if we continue. Set address, get descriptor, but it's fun, so why not? Set address, get descriptor, set descriptor, get configuration, set configuration. Same for interface, get interface, set interface, and sync frame. What is synchronization frame? Probably. And we can say that b request is a setup request, and then so USB request.set address, or that was we'll rename it to setup request. Okay, so we have a few more examples. Okay, so that's an example for get descriptor. So I guess the recipient is the device, just like this get descriptor. So setup recipient.device, and then there is like yeah, there is, what else did we have here? Type. I guess the type is standard because they don't say anything about the type here. So type setup type.standard. And we still got a few more, so W value, W index, and W length. Oh, so length specifies the length of the data to be retrieved, at least in the get descriptor. But I want the set address packet, so there must be an example here. Maybe if I will look for photos, I will find a good example. Yeah. There is like, oh, there is like an example here. It's the same website. So let's see. Device, start of reset, get device, set address. So 0. No, I'm not sure. There isn't like the data here. Isn't there like an example of set address, like the actual bytes? Setup. Yeah. A lot of charts, but no real life example. So what we are probably going to do, unless we find it, is either looking at the code to see what it expects to find there, or I guess TinyUSB has like something that sends these addresses, so we can see how it makes those addresses. I guess setup packet, maybe. Yeah, that seems good. But who fills this setup packet? Oh, this seems good. So there is like, oh, it just copies it. Let's try to look for set address inside TinyUSB. That sounds like yeah, it seems very similar to the code we have just written. But yeah, where do we, here, we initialize, yeah, this is the request that probably the host mode of TinyUSB is creating. So yeah, we can see the recipient is the device, the type is standard, and the direction is out. So out probably means host to device, which is 0. We can just double check this. Yeah, this is 0, as we can see here. And then let's go back. So this is the request, and then so we set this, and then W value is just the address, and then we have W index, which is 0, and also W length is 0. Cool. So now we should be able, isn't there like set address? Oh, too many Ds. So now we should be able to set a device address, and the same go for the set device configuration. Let's try to set configuration. Let's try to figure out what these packets looks like. I guess it's the same, and that's my guess. The CFG num goes here, just like the setup, like the set address, but there is probably set configuration. Yeah, so let's just W value is the config num, and device recipient device type standard. So recipient device type standard, host to device. This is 9, and this is also 9, and then W value get the configuration num. Yeah, maybe instead of CFG num configuration number. Yeah. Okay, cool. So we have those two pieces figured out. I don't know. Let's see if we get anything new now that we implement those two. And it probably won't do the trick yet, but it would be interesting to see if we get a different result or if we still panic. Yeah, we still panic. Probably even the same place. Yeah, but I guess this time we'll probably, we had that function, let's restart it, and we'll probably get a bit further in the USB stack. So we'll probably have the device configured correctly. Let's check this out. So that was inside USB notes, that was, or no, it was in the log, the commit here. So break here, continue, and hey Graham, nice to see you here. There is also page 413 of the RB20 datasheet. What's there? 143? 413. No. Page 1413. There was a chart, I remember, some kind of chart that, yeah. Probably this is the one you were referring to. I think I may not have the latest version, so the page numbering may be a little different. Anyway, yeah, we can see, yeah, this also shows that like the address is inside W value. Oh, pretty useful. That would have been quicker than looking through the sources. So thank you, Graham. Yeah, and now we wanted to see where we go. So next, and then it's not vendor, or so I hope. And we get to line 655. 655. No, USB device, not USB host. Okay. I think something went wrong here. We went into process control request. And then, how did we get here? We did get here, right? 655. Where is 655? Oh, that's cool. So that's setting the address. So that sounds good. And then there is, it's addressed, we can see. Yeah, we can see it's connected and addressed. CFG num is still 0, and let's just continue, and we hit the breakpoint again, and now yeah, now we can check if we go to the switch. Yeah, we can see it's reached the configuration number and assigns it to the USB, and then here inside TUD control status, we somehow get into this panic. So what happens here? So it's inside the TUD control status, and something is wrong. But what could be wrong? TUD control status. There is a bunch of them. This one comes from TUD control status. Yeah, USB control. Status phase, request, buffer, total, data length, and then it calls this one. And what does this one do? It's not if, oh, this is where it's defined. So depending on the direction, it would address one of the endpoints, and then it would probably send some information to this endpoint, I guess, and maybe we had to configure the endpoint first or something like that. Let's see, we do. If we wanted to do the entire sequence, we would need to read a bunch of descriptors, but in general, we would just need to set the address and set configuration. That's the only thing that should actually modify some stuff. And yet the code expects something to happen here that doesn't. So in this function, it checks if, what is this OR mask? So value equals 0. It reads from buffer control, and then it probably clears some bits, and then set address is the only request which doesn't get ACKed to the host. Okay, so yeah, I guess that's why set address works while set configuration miserably fails when it probably, where did it go? Oh, I just jumped to somewhere that was 414, I think. Yeah. Yeah, so that's probably why it blows up where it tries to send this ACK, but I'm trying to figure out what probably expect something to happen, but it doesn't. So what is this buffer control? This seems to be the buffer shouldn't be available, I guess. Yeah, buffer control. So is it like something that belongs to the hardware or to the software? It seems like there is an hardware register for the buffer control. Yeah, I mean, there is an easy way to check this. Let GDB help us with this. So P, that was here. Yeah, let's print this. Yeah, this is definitely somewhere inside inside USB DRAM, so it might be related to the hardware, or maybe the software manages this, but at least we know where this structure is at. Let's print EP. EP is something managed by the software, so let's see who assigns a value to buffer control. USB, yeah. So every endpoint has a buffer control register in DPRAM, and we probably need to implement that. USB, where are you? List of registers, but these registers are like not in the, oh, here it's also mentioned this buffer control, so maybe it's in the programmer's model. USB buffer, that's just buffer control register. Oh, there is this layout for the USB SRAM. Okay, so the first few addresses are used for control register containing configuration data. So yeah, so we can see at offset 0 we have the setup packet, and that's what we just did now. And then we have a bunch of registers for the endpoints. Like EP1 control to EP15 control, and then we have the buffer controls. And then we also have the buffer 0 and optional buffer 1, and then the data buffer. So let's first create for a few constants so we can use them. So there is like, it starts from EP1. All right, so setup is probably EP0, I guess. Okay, so yeah, that was in usb.es, and then let's create this So these are USB peripheral registers and USB that was DP-RAM, right? DPS-RAM registers. And then it was EP1 in control is at 8 and EP1 out control is at C, and then we have those ones can be calculated, and we have const EP0 in buffer control here, and for probably 84 for the out buffer control. Now we need to figure out what these registers look like. Yeah. So yeah, we have a few bits here, and unfortunately it doesn't say if they are read-write or not. But yeah, there is endpoint enable, single buffered, enable interrupt, endpoint type, not available, interrupt, data buffer. Okay, so this is the endpoint control, but we are not interested in that. We want the buffer control for now. So buffer control, buffer is full, only valid for double, last buffer 0 is full. Okay, the only thing I wish there was indication if these bits are like read, write, read, like are they always, I guess since it's RAM, then it's probably readable and writable, all of them. It's shared if the endpoint only the half. So how does for host the buffer full will set unsuccessful? So there are like two buffers, I guess, and buffer 0 and buffer 1, and one is yes, 0 is status from controller. So yeah, I guess we need to find out how which bits we need to control and in what way. So we see here that it's that was, where did it panic? Yeah, it wants the buffer. It probably updates it. I guess we can't really see the values. They are probably optimized out at this point. Where are we? We are at exit. Yeah, the nmask and the ormask are optimized out, but we can probably go to RB24, the USB-H, or the one that calls it, that's HW endpoint start next buffer, to see what happens there. So EP-val, and so this is set value 32, right? That was it. Yeah, set value. So this is 0 and this is value, and the nmask is 0 and the ormask is value. So we are setting the value to the ormask, and then we don't want, so if we are setting the USB buff control available, we expect it to be unavailable first. So somebody should set it to unavailable, like remove this flag. Let's see what's up with this flag. Start next buffer. Yeah, this is where we call this function from. So yeah, so we can see the code only sets this bit, and I guess it's, yeah, this is probably buffer 1 because it's the lower bits. So this is like bit number 8, 9, 10, bit number 10. Available. Can I be used for transfer? 1 is yes, 0 is status from controller. So we should change it to 0, but when should we change it to 0? Probably when the transfer finishes, I guess. Yeah, we set it here to control avail, and at this point we expect it to have been cleared. So yeah, it's a bit challenging to figure this out from the datasheet, but yeah, because there is, if it had like, I mean, I'm not sure if this available, and yeah, I guess these are like related to this buffer controller because we have full and available here. So whenever there is like in transfer, transferring data into the host, when an in token is received from the host, the request is handled as follows. If stall is set, the buffer control register, send the stall. If available and full, move to the next phase, to the phase, but which phase? Probably to the data phase. Otherwise, send knock, send data. And where do we clear the available? Yeah, the available bit is set to go to the database. Yeah, I'm not sure at which point we should clear available, and unfortunately the word available will probably appear too many times in the datasheet. Yeah. Let's try to start looking from the beginning of USB. No, it doesn't want to do it. Yeah, okay. So we are in the USB section. That's not USB, I guess. That's still PAO. It looks like PAO. So the next occurrence is here in USB. Available. Okay, that's not very interesting. Is the available? If so, unless, but where do we clear the available bit? Wait for full to be unset and available. Okay. Must be set. If this isn't the last, then wait to be set again. The controller loops from 1 to 15 and will attempt to pull any interrupt in. That's probably in host mode if it pulls interrupts. If there is available buffer. If there is. overrun. Yeah, I'm not sure we are still in 423 now. We are already in UART now. Yeah, so it doesn't really say when this available thing is unset, so I guess we should just guess, make an educated guess. 0 is status from controller, but when is this status set? So I guess we will start by setting a breakpoint in this function, I guess, to see. I think it's probably the second time that this is called. Yeah. All right, so breakpoint here. And yeah, so now we are here for the probably first time. And then there is this. And it should be 400 hexa, also a 400 hexa. And then this should not happen. And yeah, this updates the value. So this happens. Where does this happens? In EP00 len inside the set address. So yeah, so probably the set address does try to do some kind of transfer, endpoint transfer here. 0 len status probably send some. This probably sends some data. Send 0 len complete response to an EP0 in. So let's see. How does xfer work? Where is this function? So it calls it start or continue. What does start do? Here we are in start. So start, what do we do? Start transfer of len on this EP. And then it writes user buff equals buffer. Endpoint start next buffer. Yeah, it copies this somewhere. Let's see if there is like any interesting writes starting from this point. So if we just continue till the next time, no, there aren't any writes. Now it will panic. Oh, we didn't. Interesting. Yeah, probably now it will. Yep. But yeah, I'm not sure I'm seeing any writes here, so maybe just writing to the bits here is enough. And if so, we'll probably have to change the code a little. Like, isn't there like any register that we use to tell the peripheral, hey, we want you to send something? Or is it just like writing to those buffers that starts the transfer? Controller. Set buff status. completed. All right. This is a host. Let's see. Let's just print every single write so we get information about to see if the code writes somewhere into this code. So SAE set. I hope that would be simple, but yeah, apparently sending the axe complicates the things a little bit. Yeah, so console.log USB write offset to string 16 value to string 16, and let's run this again, and let's restart this as well. We wanted to break in, we can break in this start next buffer. Okay, and then yeah, so let's just make GDB read from invalid memory addresses. So yeah, so now we know where we stopped. Now let's continue and see. No, it seems like it doesn't write until it crashed. So yeah, yeah, so Graham says in the chat, and that's pretty useful, that writing into available actually starts the transfer, and then the hardware will clear the available bits once it has started it, or actually completed it. Okay, this is very useful. So yeah, this also correlates with what I'm seeing here, because the code doesn't do any other writes to the registers, to the USB registers. But this also means we would need to treat the USB DRAM not just as a buffer that, I mean, we need to be able to intercept those writes. So yeah, let's go back to the RP2040. That's USB is going to be a special case. So writing to the USB TP RAM should also, so we have write uint32, and when we are writing to the DP-RAM, let's have offset equals to this, and then we should also let it why do we return? Does it return anything? It doesn't. I don't know why we return here. So offset equals this. And we should also let this .usb, isn't there like, don't we have the USB peripheral here? USB CTRL dot dp RAM updated and offset value, just to let USB that it has been updated. And then here we can, for now, just check if the available bit is set and clear it. Later we will probably need to Graham says he thinks the reason why it works this way is probably because it's in its own clock domain or something like that. Probably things that you need to take care when you're designing the silicons, and there are like a few clocks, I don't know. Okay, so, and then we can say if offset, so if we are writing to any of those buffer controls, I think it's with 32 bits, right? I hope, yeah, it seems like. So if the offset in buffer control that was buff available. So if this bit is set, and let's define this bit, I already remember DP buffer control bits. I think I already remember it was bit number 10, I think, starting from 0. So if this is, let's just double check this, but I'm pretty sure I remember it. Now let's just find where that table was available. No, it will take a lot of time, or maybe not so much time. There we go. Yeah, bit number 10. So if it's available and the offset is EP1 and less than EP15 out buffer control, which is at const EP15 at FC, start USB transfer, and then the buffer length should be, yeah, I should have saved the number of that page, but it's probably somewhere here, the table with the bits. Yeah, there we go. So this is like the transfer lengths, those lower 10 bits. Let's also log the offset, or maybe we can already like figure out the endpoint, const endpoint offset minus EP0, and we need to divide it by 8 or shift it right by 3, and so we can say endpoint and this is the lengths, buffer lengths. Right. Okay, so start USB transfer and point lengths, and we hope this to be printed. And let's just try to sort of finish it immediately and see if this solves the panic. Probably we can also add the buffer direction and then value, and then if this bit number 4 is set, then it's yeah, if this bit is set, actually bit number 2 out, otherwise, yeah, that was out. 84 is out, yeah, so maybe buffer out true, out direction out, otherwise in. Yeah, so just so we see what happens, and then let's see if this did the trick and we can get past the USB initialization now. It didn't like, oh, not this dot value, this dot RP2040 dot USB DP-RAM at offset. Yeah, now this makes more sense, a bit more sense. And thank you so much, Graham, for your help here. I think this is really a time saver, and we still die though. EP was already available, same place, but let's see if we got any interesting prints. No, we haven't. So this is oh, I forgot to save this file. Classic. Let's restart this. And continue, and we still die at the same point. But now we do have some debug information. We see that there was a transfer on endpoint 0 in and length of 0. That was probably the maybe the direction is wrong. I would expect the direction to be out in the USB direction. Yeah, strange. Buffer control, the in comes first. And this bit is set. Oh, yeah, it's the offset that I need to look at, not here for the direction, not the failure. Yeah, yet another useless copy paste error. Okay, so yeah, so now yeah, this makes maybe more sense. I don't know why it sends in, but then it sends USB transfer out with this length, and I think we have. Yeah, we shouldn't do this. We should just clear this bit without the value. Yeah, let's retry. Maybe now it will work. Not yet. Same problem, right? Yeah. Set value inside X transfer start. And what did we transfer this time? Inside process control request. Yeah, seems to be the same place. Yeah, so let's just double check that we are calling this function after updating the buff available. If value and buff available, and we are, oh no, this is the USB. I wanted to check DP-RAM updated. Yeah, so we first of all, interesting. Yeah, that's probably the reason. We should update set uint 32. This is like a byte array, and this is way beyond the range of bytes. So .dp.setUint32 offset, and then value and true because it's Little Indian, right? Yeah, offset value. Okay, so another way, another try. I'm optimistic this time. Will it work? It didn't panic. I think we got something. Yeah, all right. So we consider like a few more transfers, one more transfer now. So we have some progress, and we can see we are in main. So we got past the initialization, and yeah, Graham says in is to host, 0 length is ACK, out is to the device. So yeah, so in is to host, so we are sending the ACK. I don't know why we had this out on endpoint 2. Maybe it's like writing the CDC data. Does that make any sense? I mean, endpoint 2 seems to be where maybe if we can take a look at the buffer, but then why doesn't it write the next buffer? Maybe we should send some kind of acknowledgement to this CDC transfer. But yeah, so where do we find the actual buffer? We know the length, and we know maybe instead of out, we'll call it, so we said out is the device. Let's in is to host out to the device. It's probably from the host perspective, in and out. So yeah, let's go back to the USB and try to figure out, or maybe we can figure it out quickly from the code. It writes into HW data buff from user buffer to hardware buffer. And where is that hardware buffer? Let's just breakpoint here and see. Yeah. No, I didn't. Let's restart the whole thing. Break here. And then we wanted to see EPHW data buff. Yeah, it's at 100 hexa. So I guess we can just print the value there. Do we have like some kind of hex dump? We don't. So for I to buffer lengths I++, and then console log and byte hex. There is like encode hex buff that we can use. And this.dp ram RB2040 dp ram slice from 100 hexa to 100 hexa plus buffer lengths. Yeah, that should probably do the trick, just to get a good understanding of what this buffer looks like. Yeah, I don't want the GDB. I want to restart this, and also let's disable, or let's enable it to just run without waiting for GDB, so we can get it output immediately. And let's see, what do we get here? Yeah, it's all zeros, not really interesting. So it's sending, the second time it's sending to endpoint 2, and then we call it set configuration, and maybe it's expecting something from us before like CDC becomes available. I don't know why did it send us all this data to endpoint 2, but it seems it just makes sense to me that, or maybe we're reading from the wrong memory address. Maybe this is like the buffer for endpoint 1. Let's go again with GDB and break. But not in the first time this function is called, rather in the second time. So break here, second time, and P, not N. Yeah, so yeah, this is EP2, and yeah, the hardware buffer is somewhere else. So I guess it's configured somewhere, the address of the data buff. Who configures this? Who configures this? HW data offset. So yeah, there is like this endpoint control register, which includes the buffer offset. So Graham says that the Tiny USB is expecting data on endpoint 2 for CDC keyboard, so providing the hardware for a buffer to fill with data which when it arrives. Okay, so it gives us a buffer, and I guess that's what it does right now, which makes sense because this is an out buffer. So
It's, yeah, having Graham here is like having a cheat sheet. That's so helpful. Yeah. So yeah, we can kill this and restart it so we see the output again. But yeah, so what's going on here, if I understand correctly, we are getting a buffer from the out is from the host to the device buffer that should probably get some data as soon as the serial port is opened on the computer, like the USB serial port, and then we should probably fill that buffer with data. So where is that? So first of all, yeah, the buffer address, we should figure it out. It was in USB. Yeah, I'm pretty optimistic we'll have it working by the end of this session. Oh no, Graham, you are never too helpful. It's much more useful to spend my time, I think, implementing, making things work than, like, trying to figure out things. I mean, we still have a lot to figure out, so every kind of help is really appreciated and well received. It's not a spoiler at all. Yeah, so yeah, we had this thing here, yeah, where we had those buffer addresses, like in the, I just need to remember where all these tables are, and then I won't have to go looking for them every time. Yeah, it's maybe in architecture overview. Yeah, this is like page 406 and 405 where the table is at. So there is EP1 control, and then in and out, and then the control register gives me the offset of the buffer in bits 6 to 15. So const buffer offset, we take this this.rp.dpram view read uint 32. So maybe first of all control reg offset, and for that we need to take this EP in 0 control plus 8 times the endpoint minus 1, because it starts from 1 and the endpoint number starts for 0, and then if it's buffer out, then we need to add 4, otherwise 0. So this should be the offset of this control register, and then we just read this register. Maybe we'll make it a bit, break it down, control reg value and true. And it's not happy because it's get uint 32. And then this is, we need to shift it by 6. And how many bits is that? The data buffer base address, so bits are ignored, so it's probably they should be 0, I guess. So it's just the lowest 16-bit, and then we can also ignore, so just 0 out the lowest bits, so lowest 6 bits, so C0, I guess that would do that. And then we can buffer offset
and buffer offset. And let's also print the buffer offset, just to make sure we got it correctly. All right, let's see what's going on now. Yeah, okay, so now I think something is wrong, because this seems correct, but oh, wait a second. For endpoint 0, I think yeah, Graham says he wrote the USB code in the root ROM, so he probably understands all the spatial implementation details of the USB controller. So yeah, I guess the endpoint 0 is always at the same offset, because it doesn't have those control registers. So maybe we should do something like that, because I remember for the code the offset was at 100 hexa. So if there is an endpoint number, then this is here. Otherwise, we'll take a wild guess. It's always here. Okay, so yeah, now the addresses make sense, and now we need to fill this buffer and somehow tell the software, and I think that shouldn't be too hard to do, that we have data for it. So we can probably do it right here for now. If buffer, or if endpoint equals 2 and buffer out, then write some CDC stuff to the buffer. CDC, I think it's called CDC ACM specifically. And then we need to see who CDC device, I guess, how this works. So prep out transaction. Yeah, it seems like this is a good place to start looking at. Claim an endpoint. And then who calls this prep out transaction? So read available. Right. Bitrate, FIFO config, CDC open, yeah, ACM subclass, and USB endpoint open, prep out transaction, prepare from incoming data. I guess this is what we are seeing, like here. This is where we are preparing. Actually, we can just verify that with a quick breakpoint. Let's comment this out so we can set up the breakpoint. Break here, continue. Yeah, and we can see it didn't print it, this thing, and now let's just finish this function. It returned, and yeah, it set up this transfer. So yeah, we can now be certain that this function actually sets up this transfer interface. So this is probably where we need to get control transfer. This is maybe where we need to get when we actually get the data, or maybe not. CDC transfer callback maybe here. So maybe we need to
Yeah, receive new data. Maybe we need a control transfer first to yeah, to configure the CDC. So we can let's see, we can set line coding, get line coding, set control line state, PSTN, public service telephony network. Is that you? Yeah. So we somehow need to get here. So if we receive the new data or data sent to host, but how do we start sending the data? Because at this point we should have some data. I mean, we can probably send some data and see what happens. Let's see. I guess this won't be called right now, but let's just make sure it's not, we are not getting there yet, because if we are, then we are very lucky. And break here. Yeah, we never get here. So we need to do something in order to get here. Probably tell the USB hardware, tell the indicate that the USB peripheral has received something. Who calls this? Yeah, I think the better way to find out would be to test it. I think we still have the same firmware on the actual device, so let's try to see if we can just find who calls this function on the actual device and work our way out from there. So let's break here and monitor reset init and continue. Yeah, everything is initiated by the host. So yeah, do I have PuTTY or something like that? Yeah, I do. But which serial port is device manager? Is the Pi Pico CDC connected to? Probably COM20, because that's the only one. So COM20, and yeah, I guess that's it. Yeah, and now we can see a few things interesting. So we already got the hello world way before we went to this callback. So the data is already there, and we can see it's called from task here in USB-D. It was line 553. Yeah, so this happens when we get DCD event transfer complete. And who calls that? DCD event transfer complete. I guess this function does it. Where do I tell it to be case sensitive? Yeah. Yeah, this function does this. So there are like a lot of places that call this function, but I guess this is in the CDC. MSC DCD. I mean, we can probably set a breakpoint here as well. Let's see who calls this one. So handle buff status from IRQ DCD RP2040. Yeah. Line
311. So it reads the status, and if there is buff status bits, then it calls handle buff status. And what is that handle buff status? Where is that? Yeah. So it goes over the endpoint num, all of the endpoints, and then I guess it does something to check interrupt remaining buffers. And then it calls, where does it call DCD event complete though? Maybe I'm not looking at the right one. In DCD RB2040.c. Oh, this is HCD, DCD RB2040.c. Yeah. Okay, so we are going remaining buffers from USB HW buff status. So there is like this buff status which tells us which buffers the card needs to check, and then it clears this bit by writing to it. So this is register is writing write clear register, and then it finds the endpoint, and then it says the transfer has been completed. So I think the first thing we need to do is find this buff status, where it comes from. Yeah. No USB HW here. Where is that? In DCD in HW and buff status, which is one up. Buff status. Yeah, this is like just the USB registers. So list of registers. Yeah, buff status. So here it's buff with a single F, and here with two Fs. That's why we didn't find it. Buffer status register that a buffer has completed on the endpoint if the buffer interrupt is enabled to be completed. Okay, so I guess as soon as we have a new buffer, we should do a few things. We should raise this, set this flag, buff status bits, and also let's, before I forget all these details, let's create a function that does it for us. Let's call it, where is that function? Private indicate buffer ready or something like that. And we have endpoint number out boolean, and then it should first of all set this bit, and then it should also set the corresponding bit in. That was this register buff status. Do we have it? No, we don't. Const buff status 58. Okay. There is also CPU should handle. I hope we don't need to take care of this now. Yeah, so there is this buff status, so we should set a bit in buff status. And we should also, before we forget, let's implement the write clear for this buff status. So case turn this dot. So this is write clear, buff status. Just clear those bits. And then we can define a private buff status. And when we read from it, turn this .buff status. Yeah, okay. And now we can go back to this indicate buffer ready, and this buff status or equals, so 1 shifted by endpoint times 2, I guess. So right, so yeah, and then +1 if it's out, otherwise 0. And then after we did this, we can also say this USB int s buff status bits. Where does this come from? Is it like a part of the SAE? Int buff status, where does it come from? In status, intro. Yeah. Let's see which bit it is. No, Pico SDK. That was buff status bits. That's bit number 4. Raised when? Where is bit number 4? I don't think it comes from this int register map, right? Int row. So who else update int row? Let's take a look at the datasheet to find out where this bit comes from. It probably doesn't come from SAE, so we may need to take care of this ourselves. Yeah, so that was this intro. Raised when any bits in the clear by clearing all the bits in buff status. Yeah, so we need to take care of it ourselves. So let's do this. Yeah, so we have int r bits const. This one is number 4. And then when we update buff status, we can do it. So this dot if this dot buff status, then this dot intro, or probably have, yeah, this dot buff status updated. We will have a method that takes care of that because we'll need it soon. We're in another place, so private, so where we indicate that there is a new buffer available. So it's very similar to this. So if this dot buff status, then we set this bit buff status. Otherwise, we clear this bit. No, that was not the address of the register. That was, yeah, int r buff status.
And then after that, we need to check for interrupts. And it's not happy about something. Oh yeah, this dot, so yeah, just buff status updated should set a bit. And now we have this indicate buffer ready, and we can probably call it with this buffer, probably just indicate that it's ready for now. Endpoint, we can say endpoint 2. I don't think it will change anything, but let's try to run it and see what happens. I mean, we have seen in the physical chip that this function that says, what was its name? This DCD, I think it was X for complete. Yeah, this one is called like after we receive the data in the PuTTY, so in this terminal. So I guess it's not the thing we need to, like, it's not the thing that will get us to the next step, but let's try that. See if we get anything interesting. Ooh, interesting. We did get something interesting. First of all, it's reading from a new register, 5C, and it also fails with a trap, so that's interesting. HW handle buff status in the higher queue. So that's a good place. That's where we wanted it to be. Let's see why it's not happy about it. Yeah, so it's running here, but then what is the assertion that it has 212? Probably this one. That's the only assertion that we have here. So if unused which, yeah, this register here. So we should be single buffered. So basically this register that we just talked about, and I see this is probably the read we are getting here. It should probably be all zeros for now. So let's do this. That was this which register, which was CPU should handle. Buff CPU should handle, right? This one is the, yeah. And then we should return, when reading from it, let's just return 0, because that's what the code expects. No, not when writing. I think it's read only anyway. Yeah. When reading from it, we should return 0. And let's retry that. And we should not crash again, but I don't think we'll, I mean, I know we won't see any interesting output, but we did crash. Is it the same place though? No, it's in a different place. Buff control, and buff control buff is full. So this is in endpoint transfer continue. I guess we should, let's do this again. It's in this function in RP2040 USB. RP2040 USB. We don't need so many windows. And line 246. No, it's not here. RP2040 USB. Yeah, there is one. And 246. 246.
X first sync. It's inside transfer continue. And then, oh, maybe it is inside transfer seek, but where do we have 246? Yeah, probably one of those assertions. Or no, this doesn't look like this. Yeah, this is like where we have the problem. I don't know why the debugger doesn't point at us at the right place. Maybe we have the debugging symbols are old, but anyway, it's the only assertion that I'm seeing here. So this must be, or no, maybe this one. Yeah, this makes more sense with the line numbers that I see here. Yeah, 246, and this is 244. Yeah, but anyway, if we are out and received, we can increase the length after appropriate. So it should probably also set a buffer to full when we receive data. So let's do that. So that was, where did we indicate? So we also want, in this case, to set buffer full. And this value is, yeah, this is like bit number 15, I guess. Let's also change this one to USB buff available. Yeah, or USB buff control available. And maybe now it won't panic. Restart. And it did panic. Where now? Ooh, in a different place. Oh, yeah. I'm not sure if inside DCD endpoint. Let's see what we got here. Yeah, no new buffers or anything, but now it's complaining that a buffer is like what we had before. Where we are set. Oh, I know. The thing is, yeah, we should probably do, I mean, let's do it like that. So we'll just update the value each time to make sure, like, we set a value here, but here we just reset it. So let's just make sure we always update the value and not override it. All right, and now maybe we'll get no exceptions. Maybe. Interesting. So yeah, we can see something interesting. We did set a buffer, and then it requested one more, and then another one more, and then it stopped. Let's see if it's, where is it? It's just sleeping. So yeah, probably it filled some kind of internal FIFO with the data that we send it, I guess, but we still don't get any data from the device. And I'm interested whether we should send something, or should we initiate this data to be sent somehow? Let's try to figure out what happens. I mean, the device hasn't set up any buffer for us to send on this endpoint, so maybe we should do something before the device does that. To figure this out, let's try to find a code that sends the data and set up a breakpoint on the physical Raspberry Pi, just like we did here, to find who calls it. First of all, we can let it continue, and then we should probably, that was here, I guess, no, in the CDC device. So it was before CDC transfer callback, but we can probably see how it sends the next packet. So invoke retransmit callback, probably this should be helpful. Or maybe not. Anyway, there is like USB endpoint transfer, so maybe just breaking here will be helpful. Monitor reset init, continue. Oh, that was quick. Continue. Yeah, I guess breaking here doesn't make a lot of sense before USB was set up, so let's disable this breakpoint, continue until it initializes, and now let's enable this breakpoint and continue again, and let's restart this session. Yeah, and the annoying thing, I don't know if it sent the hello world already or not, but yeah, we can see we are in this function inside CDC control transfer from invoke class control from process control request. Yeah, but I think just to make sure, I will restart monitor disable one, monitor reset init, continue, and just, you know, make sure yeah, enable one, continue, let's restart party. I think that was com20. Yeah, and it went away. Anyways, yeah, I think, what is this buffer? I think this is an interesting place. So it's called from process control request, and there is this packet, probably control request, that correlates with opening this serial port, and then it's inside CDC control transfer callback. So that was again in frame 3 CDC device 372. Yeah, so it sends a get line coding, which does something, returns something, set control line state. I'm not sure if this is relevant for us, like if we actually need this. Anyway, if we continue, we can see now, where are we now? Again in the control transfer, frame 3. Again in this line coding, I guess, 372, get line coding. And yeah, USB control. That's something. CDC control transfer. Yeah, I'm thinking we should probably find a better way, better place to break, to figure out where it actually, what actually causes it to send the data. That's, after all, what we are interested in, the data. Yeah, I guess it's not functioning because it's in debug mode. Yeah, so we want to find maybe CDC and write flash is something we should look at. Endpoint claim, pull data from FIFO. Oh, let's take a look at this one. Break here. Disable one, monitor reset init. Continue, and then let's open PuTTY again. COM20. Okay, this is interesting. This was called before we got any output, but it seems like the connection has already been opened. So this is called from stdio USB out cars. Yeah, so I think the first thing to do would be just to finish this. And by the time this function has been finished, we already got the hello world. So this is actually, let's write it down. This is actually the function. We don't need this anymore. Actually sends the data to the host, the serial data. Okay, this is interesting. And now let's try to debug the simulator and see if we get this function. So yeah, break here, and we don't. Interesting. So that's what we should strive to get to. So let's go back to the real device and yeah, who called this? STD. Yeah, it seems to be sort of synchronous, I guess. Not here. It's in. Yeah. So this called TAD CDC, right? Only if TAD CDC connected. So maybe we should break here in the emulator. Let's restart it and break here. Continue. Yeah, we get here, and let's see what happens here. Oh, TAD CDC connected returns false, so we are probably missing something. Yeah, it's not happy about this, but let's see what this function, I remember it from last time. What does it return? Or why does it return false? TAD CDC available. No, connected, not available. TAD CDC connected, CDC unconnected, and CDC unconnected if TAD read. Probably we need to set the line state. That's what I'm guessing. And that would probably, so there was this thing about setting the line state. So where was that? In the CDC device line state. So we probably should send a set line state right? There is set control line state, and this sends the line state. Setup or ACK. Yeah, let's try to break here and see what happens on the physical device. So back to the physical device and monitor reset init. And we want to break in CDC device.c 377, CDC device.c 377. Continue. Okay, that makes sense. And stage equals, yeah. Okay, who calls this? So it's in process control request, invoke class control. So I guess we should probably, we can probably create a function that will try to craft this packet that it's expecting. That would be, let's call it private CDC set control line state value. Let's see if Google can help us with that. Set control line state CDC. Yeah, control line DTR RDS. Seems like it's just, yeah, these are like the class request, and this is 22. Let's just make, I just want to double check that we actually need this. W value control signal bitmap, that this is the thing that we actually need to do. So again, this calls, this sets PCDC line state, and then inside when we're checking if the CDC is available, that was CDC and connected. Yeah, we are checking if this line state, and I think it's the same thing, right? If DTR, if bit 0 is set, right? That's what we are doing. It seems so. This seems to be the only place setting line state. So I guess we should set this bit. Let's see what happens on the physical device, what it sets those bits to. So again, we are here, and we want to print the value of request W value. It's 0. Interesting. Maybe it's called multiple times. Yeah. Monitor reset init. Continue. Yeah. So now let's open a connection. And we can see, let's print. Yeah, it's set to 3. So probably when the port is opened, it's called with this value of 3, which makes sense. All those 2 bits are set. So let's create a setup packet and try to figure out all the parameters. Yeah, I guess we can probably add this to, instead of write, let's call it send setup packet, and then it can also send those bits, and we don't need to take care of them whenever we send a setup packet. So
here we can just send a separate packet and set control light state, and we said that was W value. We just want it to be 3, which is DTR or CTS, right? For now. And this is host to device, and the recipient is device, and the type is class, I guess. And then the request, I think we have it here. CDC request line state 22 hexa. Or maybe we can just use a constant here. And define this. Yeah, here. USB protocol stuff. And this would be CDC stuff. Const, that was 22, right? Yeah, hexa 22. And, oh wait, we still need to send this packet. And the W value is, oh, wait a second, I messed this up a bit. Oh well. Yeah. Yeah, this is the correct one. Now I can just redo everything and fix that one. This is the correct one, and this goes here, and then I can set those. And I think W index is like the, I think I've seen this here, is the interface, and I guess this is interface 0, so that would be fine. I mean, let's try it. Interface equals 0, right? That was interface at W index. And let's also add value CDC DTR or CDC CTS. That would be the default value. And let's define those constants as well. And that was DTR. Yeah. DTR was bit 0, RTS was bit 1, just to make it a bit more readable. CDC DTR, CDC RTS, interface number, because interface is a reserved word in TypeScript, we can't use it. All right, and then so now when we set things up, let's also so we have this device configured, and then after the device has been configured, set device then probably else this dot, not sure if it's the right place to do it. Maybe CDC initialized. Yeah, just make sure it's done exactly once. And then let's have a private false, and we can have this function this.cdc initialized equals true. All right, let's see if we got anywhere with all those changes. If now we actually get into, no, we don't want to go to the Raspberry Pi, we want to go here, but we do want to copy the breakpoint erase that was here. and see if it gets here. No, it doesn't. Yeah, it still does a lot of out, but it never gets this nice request. Ooh, what happened? No, it didn't get to the breakpoint. Let's just console log set device config. Is it a standard though? It's class. Oh, that's probably the problem, where the problem lies. We sent the wrong device configuration packet. Let's restart. Break at here. And we still haven't got there. We can see, oh, interesting, but it does do more stuff, I guess. Reading from 16.8. 68, isn't it like this buffer? No, it's not. Yeah, so yeah, we set a device config. Did we mess up something? Because it's hacking this, but I don't see all the other hacks for device config. Oh, wait a second. That's the device, but we want the, oh no, what did I do here? This should be standard, and this one should be class set CDC. Yeah, I messed up the, probably already a bit tired, so I'm doing stupid stuff. Anyways, let's restart it. Oh, it did hit the breakpoint? No, it didn't. Yeah. So yeah, I don't see it sending any I don't see it sending this, calling this method, so I guess we are not getting here again. Setup rec. Nobody. Oh, if not CDC initialized, that explains why we are not getting here. All right, let's try that again. Whew, yeah, we got there. So now we are getting into this place, and I'm not sure it did what it had to do. Anyway, let's continue, and yeah. Does it, there was this CDC available. Let's see if we get something new now. This was here, so let's break here, continue, and next, and next, and where are we? Oh, finish. No, it doesn't return connected yet. Let's see why. Next, and step. So TUD ready. Does it return true? Doesn't say. Let's print the value of line state though. Maybe it will be useful. And the line state is 0. So what did TUD ready return? I mean, we can manually set this to 1. Set. And then see what does. Yeah, so now it returns true. So this means that the line state hasn't been set correctly. And now after we manually set this, we can see it's true, it's returning true, and maybe it's even yeah, it's setting that's a new line here, so it's probably starting to send the data, which is pretty cool. We just need to figure out why the line state isn't, even though we CDC set control. It's getting here, it's sending us to device, and we have seen that it goes into the breakpoint, so we are probably missing something. Let's retry that and look what happens inside this breakpoint. So yeah, CDC device 377. Yeah, we should probably be, the problem is we are at the wrong stage. What's that stage? Stage. Where is stage coming from? Setup data or ACK? This is from invoke class control. Yeah, this is always happens in the setup stage. So how can we get into the not setup stage? Where is this ACK stage? Or wait a second, did we need to be? Yeah, we need the ACK stage. So how do we get on data stage or status stage? So who calls this one? USB control X for callback. Just to make sure this is the only place where it calls stuff with this stage ACK. Yeah, it seems the only place. So we need to figure out who calls this one. Let's try to see who calls it on the physical device. Monitor reset init and then break here. And disable one, continue. And now let's enable one, continue, and reconnect. Yeah, who calls it? So it's called from within task. Frame one. So task in USBD 545 USBD 545. So we should send a DCD event xfer complete, and that happens when yeah, probably in the RP2040 there is like this RP2040 xfer complete. No, we can just again, where is that? SRC device. Probably DCD RP2040. So this happens inside handle buff status. So yeah, I guess we should also yeah, so after this is becoming complex to manage, but after CDC initialized, after this happens, it sends us an ACK, and then we should probably tell it that this buffer is ready, like the transfer has been completed. So maybe we should do it like, we should probably see this ACK here. This is probably, actually I'm not seeing any, maybe this, I guess whenever it sends us anything on endpoint 0, we can probably and buffer in, we can probably indicate that the buffer is ready once. Let's try that. Not even sure what I'm doing here, but it seems to maybe make sense, maybe not. This is on the actual Pico. Yeah, let's try this. And now stage should probably set up, and whew. Yeah, if not buff control, assert not, so yeah. Wonder why the buffer is full. Maybe we should also clear buffer is full when we are doing it. Let's try that now. Restart. And continue. Okay, we got here again, and now stage is not set up. It's ACK, and it's setting this line state finally. And if we continue, we can see that we got the data in the buffer finally. I mean, there is probably still a long way to go until, I mean, we should probably also ACK this, so we continue getting more data, because we only got this looks pretty legit. This looks like hello world in ASCII. Actually, we can probably if endpoint equals 2 and buffer out, then we can probably no, and not buffer out, we can probably, so yeah, we can probably always like ACK this. Endpoint equals 2. For now, we'll just ACK those two endpoints, and this dot yeah, where do we print the buffer? If endpoint equals 2, then we can probably call we received some data, and we can probably call some user provided callback with this const in. We can probably, I say probably too many times, but yeah, let's just const buffer equals this thing. So yeah, all right, equals this. And now we can say something like, for now, let's just, console log got serial data and buffer to string, no, new I think this works in OGS, or I think we need to create buffer from buffer to string UTF-8, and it will just print the code is as a UTF string and print the value. Let's be super optimistic and run it without GDB.
And if all works well, we should get a bunch of hello, hello, hello messages. Okay, we got one hello world. That's pretty nice. I don't know why we aren't getting the remaining hello words, but it's a nice start. I mean, we are indicating that, oh, I know, we should use the correct endpoint number here as well. Now maybe we'll get a bunch of hello worlds. Let's see. Hello world, hello world, hello world. Hooray! So yeah, we did it. So far it's only one way. I guess we can probably implement the other direction in the next session. And for now, just, clean up the code and make sure it's ready for release. So, or at least I think this is a cool milestone. So let's add a callback here on serial data and buffer uint8 array. And this is something the user can provide to capture this serial data. Thank you, Steve, for the comment. Yeah, it's nice to sort of meet the goal that we have set to get this to work in this session. So it's super nice to be there. So yeah. And there is probably a lot of things to improve here in this super weird state machine that we created, but at least now that we have this sort of working, and then this could be this dot debug probably, and just print this whole thing. We don't need to print the buffer for now. Yeah. Are there any other console log? I guess we don't need this. We know that this work. Yeah, got rid of all the debugging stuff. So, yeah, I think the other thing to do would probably to implement reading from the USB. So this is but then I'm not sure how do we go about telling the code what the size of the buffer is. Do we update this buffer lengths in this buffer register? We don't need this as well. Do we update this buffer lengths in this buffer control register, or is it indicated somewhere else? I'm not really sure, but we'll probably figure it out to do. Write incoming data to the buffer. So yeah, I guess this should also use some refactoring. So basically, I think it makes sense to provide an interface, so to send data and receive data from endpoints, and then implement some kind of USB CDC controller on top of that, instead of having that in the USB CDC directly. But I think for the basic use case, we can probably, we can probably sort of start to do this. USBs, maybe have another class here for now. Export class USB CDC. And then constructor private RPUSB controller. No, let's do it next time when I'm more fresh. But yeah, I think this covers pretty much the basics. And we have to do this to the endpoint buffer. So this is something we'll do next time. And we have this USB, and yeah, we need to commit the changes we did here, just this dpram updated callback that we now need. And yeah, we don't need this import anymore. And there are a few still unused variables. I think we don't need them because we already take care of those ins and outs. We just, yeah. Cool, 336. So yeah, yes, fit USB, implement CDC receive serial receive, and that would be what's the issue number? We had an issue for that, part of issue 66. Actually it's transmit. It's transmitting data from the device. We still need to implement receiving data from the host. We can now transmit data to the device, from the device to the host. We still need to implement receiving data from the host. Let's also update this file so that it also MCU USB controller dot on serial data. Then just check that the interface is wired correctly before we commit. If it is, we should see the prints from the USB. Yeah, we see them on the console. So this is how we wire it. Usage example. Not going to commit this for now because right now it runs the allow UART, and until we have the USB more in shape, I won't commit it. So, oh, I hit the commit button. I will have to, okay, yeah. Okay, so now we also have a usage example, which is pretty cool. Maybe instead of MCU RP2040, that would be more representative. And yeah, we can commit and push. And there is like another bug fix from yesterday. If we git log, we can see the other bug fix from yesterday in the pipeline. So I'm going to release it as a patch release. The USB is not really ready, so it won't be a minor release. So let's publish this. And while I'm good with those files, so that would be a patch release. And while it's releasing, we sort of got it to work in the very last moment, which makes me happy. I'm happy that things worked out. Next week we'll continue with two things. First of all, the other side of the other direction of USB CDC, also sending data from the host to the program, and then we can probably try CircuitPython. I already have it ready and compiled, so as soon as we have bidirectional, actually we'll try MicroPython first, just because we know it works with the serial, so we'll try the USB version. And it's not happy about those files, so let's just stash them for now. And yes, save all and stash, I guess. Doesn't matter. And again, release. So we'll probably try MicroPython and see that it works, and then we can move ahead and try CircuitPython. And the second thing that I really want to do next week is also tidy up this code and provide some kind of more generic interface, so users can attach their own host device to the USB with mesh storage or whatever. We will just provide the lower level interface. So I hope that you enjoyed this session, and I hope that you have a great week. and see you next time on Tuesday. And until then, have a great rest of the week. Bye bye.